In the previous section, we talked about the energetics of solution formation, and we also talked about like dissolves like. And one question that didn't pose then, because I knew it was coming up in this section, was, well, what about these ionic compounds? So in this case, we have potassium and chloride ions being very strongly attracted to each other. And we talked about the force of this attraction in previous chapter being called the lattice energy. So there's a lattice energy that holds these things together. And potassium chloride has an extremely high melting and boiling point. Well, how is it possible that if potassium chloride has such a high melting and boiling point that we can actually get it to dissolve in water at room temperature? And we talked about in the previous section, there must be some attraction between the solvent, water, and the solute, chloride and potassium ions here. So if we look at this, you can see how the water molecules are aligning themselves. The partially positive hydrogen is attracted to the negative chloride, and the partially negative oxygen is attracted to the partially positive potassium. Or, excuse me, the positive potassium is not partially positive, it's fully positive. And this is so-called a solvation, okay? So this potassium ion becomes solvated. And it turns out that you can actually fit quite a large number of water molecules around the potassium and the chloride, and these attractive forces add up because you have a lot of water molecules attracted to the positive and the negative ions, and that's how these ionic compounds are able to dissolve in water. But what's important to note here is that what you actually have in solution is no longer KCl. What you really have in solution is K plus aqueous and Cl minus aqueous, as you've seen in previous chapters. So this is a little bit of a reminder, and this is a little bit of an explanation of how that looks at a molecular level. So if we look at the next slide, it actually asks us to draw what is formed in solution for each of these things. And as usual, I'm going to switch over to the camera in order to do that. So if we look at calcium, calcium is a 2A metal. So in ionic compounds, it's going to be 2 plus. So what we get is Ca2 plus, and that is aqueous because it's dissolved in water. And we're also going to get chloride, Cl minus, because it's in 7A, it's 1 minus, and it is aqueous. To balance it, there's 2 Cl's here, so we need 2 Cl minuses over here. And these are kind of like reactions, although you could argue this is just a change of state, but we do write it like a chemical reaction. What happens if we have a polyatomic ion like sulfate? Well, if we have a polyatomic ion like sulfate, it actually doesn't break up. So sodium sulfate is a soluble ionic compound. Sodium's a 1A metal, so we get Na plus aqueous, and we get SO4 2 minus aqueous. Again, we have 2 NAs, so we need 2 Na pluses, so we balance by simply putting a 2 in front of it, like so. And in the last example, we talked about ammonium nitrate in a cold pack. Well, here we have ammonium carbonate. Well, what does this break up into? What we end up with is NH4 plus aqueous plus CO3 2 minus aqueous, like so. Okay, and it turns out these two things can actually react together, but temporarily we might end up with these two things. And in order to balance it, we have 2 ammoniums here, so we need 2 ammoniums over here. So when ionic compounds break up in, or when they're dissolved in water, they break up into their ions, where the positive ion is attracted to the partially negative oxygen, and the negative ion is attracted to the partially positive hydrogen of the water molecules. In the next slide, what we want to look at is electrolytes. So you may have heard the term electrolyte before when you're thinking of a sports drink like Gatorade. And Gatorade is said to be an electrolyte. And what that means is it literally can conduct electrical current. What it means practically, though, is that it has salt dissolved in it, mostly sodium chloride and a little bit of potassium chloride, because that's what our body needs. If we sweat, we put that back in, and it helps us in athletic performance. And the reason for this is because it breaks up into its ions, it's actually able to transfer an electrical charge. So let's look at three different examples. Okay, the first is ethanol. Ethanol is CH3CH2OH. Ethanol does not break up when it dissolves into ions. How do I know that? Because ethanol is a covalent compound. It does not contain a metal or a polyatomic ion, so this is a covalent compound. Covalent compounds do not break up. So ethanol, although it mixes with water, all right, it should say miscible, probably better is a better word than soluble, okay, it does not break up into its ions, and because it doesn't have ions, and therefore it cannot attract an electrical charge. It cannot conduct an electrical charge, and it is said to be a non-electrolyte. Now, let's look at KCl. KCl, as we talked about before, breaks up into K plus and Cl minus. These ions can transfer an electrical charge. The light bulb is on as opposed to off over here, and we call this a strong electrolyte. I'm not going to talk about this too much because we haven't talked about acids very much to this point, but if you have a weak acid, like acetic acid, this is the acid found in vinegar, this is a weak electrolyte because it dissociates slightly, okay? And we'll talk about equilibrium reactions, and in fact, we'll talk about acetic acid in equilibrium reactions, which that'll make more sense later. So, electrolytes, strong electrolytes, are ionic compounds that dissolve in water. Covalent compounds that dissolve in water are non-electrolytes, and weak acids, which again won't come up here, are weak electrolytes. The last thing I want to talk about is the temperature dependence of solubility. And I find this chart to be relatively interesting. Okay, if we look at some compounds, like sugar, the temperature goes up, as the temperature of water goes up, here we have 0 to 100, this temperatures at which water is a liquid, the solubility goes quite a bit up. If you look at potassium nitrate, it's even more. Somewhere around, I don't know, 15-ish grams will dissolve in 100 milliliters of water at 0 degrees, and over 220 grams will dissolve at 100 degrees. There's a huge difference in the amount that it will dissolve depending on the temperature. But generally speaking, these all move in the upward direction. So solids tend to become more soluble as temperature increases. An interesting example, because it's so common, is NaCl. There's a relatively small difference in the amount of NaCl that will dissolve, okay, in water depending on the temperature. Said another way, the line is pretty flat. And here's an interesting one where we have Ce2 sulfate. In this case, the solubility actually goes down. But these compounds are not super common, but they do exist. So generally speaking, as temperature increases, the solubility of the solid increases as well. So in this section, we talked about what happens to ionic compounds when they dissolve in water, and what an electrolyte is, and the general trends in solubility of solids when we change the temperature.